Here is a strange mathematical paradox in networking. If you take a subnet mask of /24 and increase it by a single number to a /25, you don't gain address space. You actually cut your available network exactly in half. To understand why, we have to start with the baseline rule of the Internet Protocol. Every IPv4 address is exactly 32 bits long. This represents a fixed, finite total space. You cannot create more bits. You can only decide how to use them. This diagram shows a subnet mask dividing that 32-bit address into two groups, the network prefix on the left and the individual hosts on the right. A /24 mask allocates exactly 24 bits to the prefix, leaving exactly 8 bits for the hosts. Because the total space is rigidly locked at 32 bits, the relationship is a zero-sum game. Every time you add a bit to the network prefix, you steal a bit from the host capacity. That is why increasing your prefix number results in a smaller network. Let's visualize a standard 192.168.1.0/24 network. It forms a single block containing exactly 256 total IP addresses. By changing that mask to a /25, we borrow one host bit. That physically slices our 256 address block in half, giving us two separate networks of 128 addresses. Move the prefix to a /26, and the block slices again, creating 4 distinct networks, each containing 64 addresses. This creates a predictable scale. As your prefix rises from /24 up to /30, your total host capacity per network drops from 256 down to just 4. Inside any of these newly created blocks, the internal anatomy is strict. The very first address is the network ID, identifying the subnet itself. The very last address is the broadcast address, used to communicate with all devices in that block. Because these two addresses act as structural bookends, neither can be assigned to a computer or router. You must always subtract 2 from the total block size to find your actual usable host IP addresses. To find these exact boundaries without writing out 32 bits of binary code, network engineers use a mathematical shortcut. Block size equals 256 minus the decimal value of the subnet mask. Let's calculate the boundaries for the IP address 192.168.10.70 with a /26 mask. A /26 gives us a decimal mask ending in 192. We take our constant, 256, and subtract 192 to get a block size of 64. With a block size of 64, our subnets start at 0 and jump in intervals of 64, 0, 64, 128, and 192. The address we are evaluating, .70, falls squarely inside the block that begins at 64. Let's test this. Pause the video. Using a starting point of 64 and a block size of 64, calculate the exact network ID, first host, last host, and broadcast address for this subnet. Here is the mouth. The network ID is the starting line, .64. The first host is .65. The broadcast address is .127, exactly one number before the next block of 128 begins. That makes the last usable host .126. Relying on this simple subtraction method removes the friction of binary conversions. It gives you a fast, error-free way to calculate network boundaries on the fly. Let's clear up a few common traps. A /24 prefix does not mean the network holds 24 hosts. It means 24 bits belong to the network, leaving 8 bits to provide 256 total addresses. Next, do not confuse Layer 2 with Layer 3. While VLANs and subnets are often paired in design, they operate on completely different structural levels. VLANs isolate traffic at the switch, while subnets route IP traffic across the network. Let's check your retention. What is the total address count for a /25 subnet? It is 128 addresses. Now, what is the block size of a subnet mask ending in 224? 256 minus 224 gives a block size of 32. Subnetting is simply the act of drawing new boundary lines within an existing, finite IP space. Mastering these static block sizes is the required foundational step. Once you can calculate these boundaries naturally, you are ready to apply them to variable length subnet masking, which we cover in the next video.